Good morning, students. Beta, last time we did the interference phenomena and I covered all the topics of the interference. Now our next topic in wave optics is diffraction. And in my today's lecture, I only make you understand the meaning of diffraction. Now let's start. Beta, diffraction means bending of waves. Diffraction means bending of waves. When I say waves, waves can be of any type. It can be sound waves, it can be ocean waves, it can be light waves. So we can say diffraction means deviation of waves from their path. Deviation of waves from their straight path. But we know that light travels in a straight path and we called it as the rectilinear propagation of light. And whenever light travels in a straight path and if an obstacle comes in the path of the light, then it casts its shadow. By shadow we mean corresponding to this, that shadow is a complete dark portion or dark region. Then this is a dark portion, but it's like when sunlight falls on you and you see your shadow, and the size of your shadow depends on how light is falling on you. So in order to have a clear idea of diffraction, means how light is bending, let us suppose okay, now I'm going to show you how light bends, because diffraction is bending of waves. But let us suppose that there is a slit or aperture, and in front of the aperture there is a screen, and here is a source of light, and now the light coming from this source, it goes like this, it goes like this. When it falls on this slit or this aperture, it travels straight and it moves towards the screen. And on the screen, this portion, suppose this portion, if I name it as OA, this whole portion is illuminated or there is a brightness on the screen. But when light falls on this obstacle, it reflects back. When it falls on this obstacle, it reflects back. So corresponding to this part of the obstacle, we will see a complete darkness on the screen, because here we are considering that light is traveling in a straight path. So corresponding to this portion, suppose this is OX and this portion is AY. So this OX and AY portion is completely dark because light does not reaches here because of this obstacle. But same thing will happen if there is an obstacle and here is a source of light and here we have a screen. The same thing will happen here. The light rays emitting from this source, they will reach the screen like this. From here and here they will reach the screen. The rays emitting from here, they goes towards the screen, and this portion is bright. This portion is, it goes like this, it keep on going like this. Then this portion is bright on the screen. But when the light falls on this obstacle, it does not, because we are considering here the obstacle as a opaque. Opaque is a substance through which light does not passes. When the light falls on this obstacle, it does not passes through this obstacle, it reflects back, and corresponding to this obstacle, this portion of the screen is completely dark. But this what I explained here, it's according to the rectilinear propagation of light, that as we say that light travels in a straight path, whatever comes in its way, it casts its shadow, means that portion is completely dark. But when it was observed and when it was done experimentally, it has been seen that this dark portion, or we can say the shadow portion, is not completely dark. That it has been seen that light enters into the dark portion. If here is it's not like light spreads into the whole dark region, it's like that it covers the small portion of the dark region near the corners of the obstacle. If here is an obstacle, it covers the small portion. This portion supposed to be dark, but it has been observed experimentally that this portion is not completely dark. There is some light in this portion, and same here. This portion was supposed to be dark, but there is some light in this region, and same thing will happen here. This portion is not complete dark, this much portion OC, in this region OC there is some light, and in this region AP there is some light. Now what we see here, that light enters into the shadow region or light enters into the dark region. Beta, this phenomena that light enters into the dark region when it passes through the aperture, or it passes through the, when it falls on the slit, it was recorded by a scientist named Francisco. Francisco was the scientist who recorded this, that when light falls on aperture or on obstacle, it enters into the shadow region. This was observed by Francisco, and he also and according to him that this thing will happen only if the size of the aperture or slit or obstacle, it all depends if the size of the obstacle is comparable to the size of or to the wavelength of light falling on this, to the wavelength of light falling on slit or obstacle. This thing will happen only if the size of the slit is comparable to the wavelength of light. If it is comparable, size is comparable, then you will see some light in the shadow region also. If it is not comparable, then you will not observe this thing in the shadow region. Beta, diffraction is also like interference. We also observe the pattern of dark and bright bands on the screen, and we will do this later on. But you can also observe this diffraction pattern yourself. Okay, let me tell you what you have to do. Do one thing. You just hold your hand. You just hold your hand in front of the source of light, whatever you have in your room. You have a tube light. Just keep your hand in front of the tube light. You need not to go close to the tube light. Just sit wherever you are. You just keep your hand in front of the tube light. Okay. Now do one thing. Bring your two fingers close to each other. Slowly bring them close to each other. When you bring them close to each other, just do one thing. You can see this much space in my upper one. I'm holding phone in my another hand, so I cannot touch. You can see this much space, the small space in my finger. Yes, this much. Now you can see this small space in between my fingers. Now when this much space is left, you just close your one eye, and now you will see a series of dark lines. You will see, you can do yourself, and you will definitely see a series of dark lines parallel to your finger, and this is what diffraction. This will you observe. You can also observe this thing. Okay, you can also do one another thing. Just do one thing. You just turn off the light of your one room and turn on the light of your another room. And if the door is open, you will see that light enters into your dark room, and there is brightness in your dark room. Now what you have to do, you just slowly close the door of the room. Now you have to close it in such a way that only a small opening of the door is left, means a very small gap is left. Then you will see, if you will see near the gap, you observe it very carefully, you will see the lines also there. You can do it yourself, you will definitely see these lines. And all this is due to bending of light at the corners of the obstacle and spreading into the region of the geometrical shadow. But in our day-to-day life, there are many phenomena of diffraction, but we cannot easily observe these phenomena. It's not possible for us to easily observe these phenomena. Why is it so? We can observe it only if the size of our obstacle is comparable to the wavelength of light. The light which we are having in our day-to-day life is visible light, and all of you know the wavelength of visible light is in nanometer. It is of the range of 380 nanometer to 760 nanometer, and the obstacle you are having at your home, like your doors, your windows, and they are of the size of meters. So you cannot easily observe this diffraction, although it is there, but it's difficult to observe because of the size of the things we are having at our home. But this phenomena is very easily noticeable in case of sound waves. Like, when you are in one room and your mother is in another room, when your mother calls you, you can clearly hear the voice of your mother. Do you ever think why is it so? Why you clearly hear the voice of your mother? Because the sound waves easily bend and it reaches towards you, because the size of the obstacle, by obstacle I means the size of the door, the size of the window of your room, is in meter, and the wavelength of sound is also in meter, and the wavelength of sound, you know, it is in meter. It varies from 15 meter to 15 nanometer, so its range is in meters. So you can easily observe the phenomena of sound waves in your day-to-day life. Now the next thing about diffraction is of two types. Beta, is it clear to you? By this observation, what is the definition of diffraction? What diffraction is? So diffraction is bending of light waves around the corners of the obstacle and spreading into the region of geometrical shadow. So this is the definition of diffraction. But a diffraction is of two types. In your syllabus, it's Fraunhofer diffraction. Diffraction is of two types. One is Fresnel diffraction, another is Fraunhofer. The pattern which was recorded by the scientist Francisco, was later studied by this Fresnel. So in beta, the difference, oh, it's blur, now it's clear. Beta, okay, let me sit properly. Okay, see, what is Fresnel diffraction? In both the patterns, when we say diffraction, you will when you study in your next lecture, you will see, like interference in diffraction, there is also a pattern of bright and dark bands on the screen. In Fresnel, in this type of diffraction, the source the source the source, this is, suppose this is a source, this is a slit, and this is my screen. In Fresnel diffraction, this source is placed close to the obstacle. This is slit or the close place to the obstacle. There is a finite distance between the source and the obstacle, or we can say there is a finite distance between the source and the screen from the obstacle. In it, there is a finite distance between source and screen from obstacle. And beta, in this type of diffraction, we don't need any lens. I will tell you when I'll just now what Fraunhofer diffraction is. Fresnel diffraction, we have the light which is falling on the slit. It is in form of it is called wave front. So in Fresnel diffraction, the shape of the wave front is either spherical or cylindrical. The wave front is either spherical or cylindrical. This is our Fresnel diffraction. And beta, in the Fraunhofer diffraction, this diffraction take place only when the source of light is at infinity. And or we can say, suppose there is our slit, the source is at infinity. The source, this is at infinity. Source of light is at infinity. Or we can say that the distance between the source and the screen from the obstacle is infinite. Distance between source and screen from obstacle is infinite. So as the source is at infinite distance, so in this type of diffraction, the shape of the wavefront is plane, because if these are the rays, then the shape of the wavefront is plane. So here the shape of wavefront is plane. Now so beta, as the source is at infinity, so to observe this type of diffraction, the Fraunhofer diffraction, because if the source is at infinity, the intensity of the light rays which reaches towards the screen, it will fades away with time. So what we do, we keep a lens between the source and the slit. We keep the source, basically we keep the source on the focus of the lens. It's like this. When the rays are coming parallel, we keep a converging lens, so such that the source is at the focus of the lens. When source is at the focus of the lens, then what will happen? The rays, after passing through this, the rays which will pass through this, it's like that after passing through this, they are parallel. It's like after passing through this, they are parallel to the principal axis. When I say parallel, it means it looks like they are coming from infinity and they fall on the slit. And when they fall on the slit, then there is also another lens, so that after falling on this lens, they converge at one place on the screen. Beta, this Fraunhofer diffraction is also called as far field diffraction. This is our far field diffraction. and as there is a finite distance, so it is also called as near field. It is called as near field diffraction. So this diffraction we will study. Beta, it's difficult comparatively. It's difficult to study this Fresnel diffraction. It's not difficult, but comparatively, in comparative to Fraunhofer diffraction, and in your syllabus it's Fraunhofer diffraction, not Fresnel diffraction. So we'll study the Fraunhofer diffraction later on. So this type of pattern or this type of diffraction you will study in diffraction at this single slit or due to double slit. This is we will study in Fraunhofer diffraction in single or the double slit. And this type of diffraction we studied we can study this diffraction, Fresnel diffraction, at due to narrow wire or due to straight edge. Okay, beta. So this lecture is all about what diffraction is. Thank you, beta.